Swayam Prabha. Digital India. Educated India.
Okay, so we will get started. We derived the differential form of linear momentum balance, and we are proceeding towards the Navier-Stokes equation, and during that path, to understand total stress in fluids, we took the first diversion to solid mechanics, the first time we travel in this through this arrow mark, and then discussed stress in solid mechanics, came back to fluid mechanics and understood total stress. Then we need to understand strain rate. So, once again we took a diversion to solid mechanics, understood strain and extended that to strain rate in fluids. Okay. Now, we are going to take once again a diversion to solid mechanics, the third and the last time. What is the reason? We need to relate viscous stresses and the strain rate or the velocity gradients through the Newton's law of viscosity. But before doing that, we will relate stress and strain through Hooke's law by going to solid mechanics for the third and last time. Okay. So, objective of this lecture is to discuss about Hooke's law. We are going to take a diversion to solid mechanics, discuss about Hooke's law, and then of course follow it later on by coming back to fluid mechanics. So, in terms of the journey to the Navier-Stokes, we derived the differential form of linear momentum balance. We had surface forces on the right hand side. To understand that, we took the first visit to solid mechanics, understood stress vector, stress tensor, and came to fluid mechanics, understood total stress in terms of pressure and viscous stresses. Then we could complete the differential form of linear momentum balance including the right hand side with the viscous stresses, with the viscous stress terms. Now, those viscous stress terms had to be expressed in terms of velocity gradients, that is where we discussed closure. To understand velocity gradients, need to understand about displacement gradient. So, we made a second visit to solid mechanics, understood strain, displacement gradient, and then the strain tensors. Then extended that knowledge to fluid mechanics, understood normal strain rate, shear strain rate, velocity gradient, and the strain rate tensor or the deformation rate. Now, we need to look at the actual relationship between the viscous stress and the velocity gradients, which is what we are going to do here in Newton's law of viscosity. But before that, like in the previous cases, we take a third visit to solid mechanics, discuss this block which is Hooke's law, which is the relationship between stress and strain relationship. Okay. Once you understand that, the analogous relationship of fluid is stress and then strain rate, that is the overall idea. Okay. So, third visit to solid mechanics. In terms of titles, first we discussed about internal forces and stress, second visit we discussed about deformation and strain, and third in this visit we are going to discuss about Hooke's law, which relates stress and strain. Okay. What is the outline? First we discuss about assumptions and then derive the 3D version of Hooke's law. Hooke's law in a simpler form should be very well known to most of us. We will derive the 3D version of Hooke's law. Okay. Now, question arises, why do we discuss assumptions now? The first bullet says, or the one of the point of discussion says assumptions. Why are we discussing assumptions? Okay. Now, what is the overall objective I have a solid body, I is subjected to some force and I am interested in seeing the response of that body, which means that which is called the mechanical behavior of the solid object. I need equations that describe the mechanical behavior of the material, and moment we talk about a material, we need to bring in properties of the material. Okay. When we first came to solid mechanics, we discussed about surface forces, surface stress vector in terms of stress tensor, and throughout the discussion we never focused on what material we are discussing about. We just discussed it could be a plane inside a solid object, and then we characterized that intensity of force in terms of stress. Then we came to strain. There again we when we came to strain, where we discussed about change in length, change in angle, which we call as deformation, quantified that in terms of strain. There again we did not discuss about the material at all, we discussed in terms of quantification of the deformation, and now we have to relate this stress and strain, and when we are going to relate this stress and strain, then the property of the material has to be brought in. Okay. So, while stress and strain are can be discussed without reference to any material, the stress strain relationship becomes material dependent, okay. And that is why we are discussing about the assumptions. When we say assumptions, the stress strain relationship which we are going to discuss is limited to that particular set of assumptions. If you recall back about stress and strain independently, we hardly had any assumptions throughout our discussion, they were all exact relationships, okay. But when we discuss stress and strain, it is with reference to a particular material, and that is where assumptions are brought in. Okay. Okay. Now, is this stress strain relationship, can it be derived? We can derive the form of the expression, but when you derive, there are some constants which you call as material properties. One material property which is known to you is Young's modulus, okay. But that Young's modulus has to be determined by experiments. So, the stress strain relationship that with the actual values of the parameters is determined by performing experiments in the laboratory, and hence the stress strain relationship is empirical. When I say empirical, it is based on experimental observation, based on experimental evidence, okay. And what is that more importantly we are doing? We are relating a immeasurable quantity with a measurable quantity, and that is the key, that is why I highlighted here. When we discussed about stress, it is certainly a very physically meaningful quantity, no doubt about it. You had a surface, what is the force acting on the surface, stress vector, stress tensor, etc., perfectly very much meaningful, but we can't measure stress components of stress, okay. But remember, when we came to strain, we said we have a plate, there are some coordinates, difference in coordinates, so which means that, and then we analytically derive the expression for different normal strain, shear strain, which means that you can measure strain and then quantify strain based on measurements. Even the questions, if you recall back, some coordinates were given, initial coordinates, final coordinates are given, which means they are measurable values. So, strain is measurable. So, strain is measurable and stress is immeasurable. By finding a relationship between stress and strain, you are expressing we are expressing an immeasurable quantity in terms of a measurable quantity, and that is the key. Stress is not directly measurable. By expressing in terms of strain, it becomes indirectly measurable. You can determine stress, you can calculate stress, but not directly measure stress, okay? And that is the key here, okay. So, to summarize this, while stress and strain discussion is independent of the material, the relationship between stress and strain depends on the material, okay. Because the response depends on whether, for example, if you take a solid, if it is made of steel, it has some response, if it is nylon, some other response. Let us say aluminum it has some other response. So, properties of the material have to be brought in, and that is where we discuss assumptions. Okay. So, what are the assumptions? When I say assumptions, the stress strain relationship is valid only under this set of assumptions. We never had this restriction when we discussed about stress separately and strain separately. Okay. Of course, for strain we said it is infinitesimal strain, that was a small assumption when we discussed for solids, and when we went to fluids even we said that is not even assumption. Okay. So, now what is the first assumption? The material is homogeneous. What does that mean? If you take a let us say a solid object, these the properties which are going to experimentally determine. When I say properties, I mean material properties. Okay. What are the material properties? We will come across few material properties. One which is very well known to us is the Young's modulus. Okay. So, if you take at every point in the body, the value of the material property, for example Young's modulus, is same. So, look at the definition of a homogeneous material, same material property at all points in the body. So, any point you take in the body has the same value of material property. What is shown in this diagram is just a magnified view of steel. So, if you zoom in and zoom in, of course, there can be non-homogeneities, but on a macroscopic scale, if you look at steel as such, then you say that the properties are same at every point. Okay. So, that is the level we are looking at. We are not magnifying and saying going to say that there can be non-uniformities from point to point. We are not going to go to that level of magnification. If you are given let us say a steel block like this, and you say at every point it has same material property. Okay. So, material is homogeneous means same material property at all points in the body. Okay. So, that is the first assumption. So, the Hooke's law which I am going to derive is for a homogeneous material. Second assumption, material is isotropic. What is isotropic? Let us read the definition. Same material property at a given point in all directions. The key is at a given point in all direction. When we discussed about homogeneity, we said same property at different points, at all points in the body. When we discuss about isotropic assumption, the same material property, you are at a given point, but in let us say x direction, y direction, z direction, all the directions you have the same material property, for example Young's modulus. So, independent of the direction, the material is assumed to have the same material property. Okay. And which means that exhibits the same behavior at a given point in all directions. Why do we say this? The property determines the behavior. So, when the property is same in all directions, exhibits same behavior at a given point in all directions. Okay. And the other way of putting this is no preferred direction. When I say that at a point the property is same in all directions, there is no question of talking about direction at all. So, there is no, when do you have a preferred direction? When the property is different along different directions, then there is a question of talking about a preferred direction, but because the property is independent of directions, there is no preferred direction. Okay. What is shown here is an example for anisotropic material. One of the examples for anisotropic material is wood. Okay. Now, what is shown here are fibers, and the wood, let us say a block of wood is subjected to a tensile force. Now, the behavior, mechanical behavior of wood will depend whether the tensile forces are aligned along the fibers or they are perpendicular to the fibers. Okay. Even if you look at, let us say, just make a simple Google search, let us say if you say Young's modulus for steel, you will be given one value of Young's modulus. But if you let us say search for Young's modulus of wood, you would get Young's modulus of wood along direction, tangential direction, longitudinal direction, which means that the Young's modulus depends on the direction. Okay. Such kind of materials are called anisotropic materials. The Hooke's law which we are going to derive is not applicable for anisotropic materials, but anyway we are safe that remember we will see shortly that isotropism is a very convenient assumptions. convenient assumption. If you do not do that, we will have really lot of difficulties. Okay. So, but in general we can, for our scope, or most of the cases we can assume the material to be isotropic. So, just to summarize, homogeneous refers to same material property at all points throughout the which means throughout the body. Isotropism refers to direction, you are in the same point, the material property is same in the all directions. Okay. That is why the terminology says isotropism, okay, no preferred direction. What is the third assumption? Material is elastic. Okay. What is the meaning of that? At any given point in the material there exists a direct relationship between stress and strain, and that is what is shown here. You have a some relationship, it could be nonlinear or linear. What is shown here is a stress on the y axis, strain on the x axis, and you have some functional relationship tau as a function of epsilon. So, at any given point in the material there exists a direct relationship between stress and strain, okay, which means that tau is a function of epsilon.